Okay, so it is my great pleasure to introduce Noumi-san, Professor Noumi from Kobe University, Japan. And it is also a great pleasure because he is the inaugural speaker in this new series of online seminars that Giorgio in particular and I alongside him have started. Because there are so many online seminars going on now around the world, but many of the timetabling for those seminars are difficult for people in the East and in Australia. So we thought we could have a very nice series with speakers from around the Asia-Pacific region. So I'm glad to see so many people here on this online seminar today. So Professor Noumi is very well known to most of you. He is a long-standing great figure in mathematical physics and representation theory. I think I'll just say very briefly that I met him, I think in 1999 at RIMS in Kyoto, when he gave a very nice talk on the symmetric forms of the Panové equations. And then, of course, many of us know his wonderful book, Panové Equations Through Symmetry, which was published as a translation of the American Mathematical Society and is still the main reference, I think, for looking at the symmetry theory associated with the Panové equations. He has recently been invited to visit the Department of Mathematics as visiting professor at the KTH Royal Institute of Technology in Stockholm, where they'll have a year-long program in areas that intersect with his interests. And without further ado, let me invite Noumi-san to give his talk on perturbative eigenfunctions for the elliptic Ruijsenaars difference operators. Please.
Thank you, Nalini. So thank you very much for a very kind introduction. And it's a pleasure for me to have a chance to give a talk at a newly organized seminar. And thanks, Nalini and Giorgio. And the title of my talk is already Nalini mentioned, Perturbative Eigenfunctions for the elliptic Ruijsenaars difference operators. Oh, yes. As maybe Nalini has already suggested, if you have a question, please write it in the chat, and then maybe that question will be picked up or I'm not sure, but please do so. And
thank you for mentioning that. Yes,
yeah.
I will pick it up and mention it to Noumi-san if he hasn't noticed it already.
Yeah. So the subject of my talk is related to in the category of quantum integrable systems, and so this talk, I hope this talk will fit to the main theme of this seminar. And maybe I guess the audience has a diverse background, so I will speak a little about the background of this subject. And as I mentioned, this is a topic in the theory of quantum integrable systems. And maybe in the physics term, it is, to be more specific, it's related to one-dimensional integrable quantum many-body problems of Calogero-Moser or Calogero-Sutherland type. So that is one description. And in such from mathematical point of view, such an integrable system, quantum integrable system, is giving a family of commuting linear operators, and the mathematical problem is to find the joint eigenfunctions for them. That is a very simple description. But and also there are two classes of quantum integrable systems to be distinguished. One is a differential related to differential equations, and the other difference equations. And as to the Calogero-Moser type systems, I don't know it will be in the middle of 1980s, that Perelomov and Olshanetsky gave a classification of such a quantum integrable system in the differential case, which have some kind of wire group symmetry. And it was in 1987 that Ruijsenaars, Ruijsenaars is the main name of this talk today, found a family of commuting difference operators, including the three classes of rational, trigonometric, and elliptic. And so the elliptic Ruijsenaars operator, difference operator, is this family of commuting family that was introduced by Ruijsenaars in 1987. And the main problem is to find the joint eigenfunction. But anyway, so this is the first page, title page, ICE. So for some years, I have been working with Edwin Langman from Sweden, KTH, and with Junichi Shiraishi from Japan at the University of Tokyo on the analysis we are investigating the eigenfunctions for the Ruijsenaars these Ruijsenaars systems and kind of its generalizations. And so I think I will report some recent progresses of our collaboration. And in particular, I'm going to propose two classes of perturbative. I will explain what it is now later. Perturbative eigenfunctions for this class of elliptic difference operators, which are elliptic deformations of Macdonald polynomials and those so-called asymptotically free solutions, eigenfunctions in the trigonometric cases. So in the next page, wait a moment. Oh, that it happens something like this always. So I gave some references here, and the first one is the Ruijsenaars paper that I mentioned already. It's 1987. And the next one is a Macdonald, the book, Symmetric Functions and Whole Polynomials. It's a Bible of the Macdonald polynomials theory. And also, yeah. So Macdonald polynomials arise as a trigonometric limit of the Ruijsenaars system. And maybe you can call it the Ruijsenaars-Macdonald system. But the Macdonald polynomials are eigenfunctions that describing the systems. And after this, Shiraishi and I did some work on the asymptotically free solution. I will explain what they are later, but around 2012. But one very interesting paper appeared last year, that's Shiraishi's paper. So number 4, affine screening vertex operators and so on. And he proposed a new kind of non-stationary Ruijsenaars function as a formal power series of the so-called Nekrasov-Pachon function type, and which he supposed that should be the main eigenfunction for the non-stationary Ruijsenaars function. I will give a comment later if I have time. But so after this, Langman, Shiraishi, and I started collaboration. And one paper is already appeared we already uploaded one paper, in archive. This is number 5. And also another paper is in preparation. So what I'm going to talk today is about the 6th paper, which is not appeared yet, but that will appear soon, I hope. Okay, so here's the content of my talk. And after explaining what are the elliptic Ruijsenaars operators, and I will go back to the trigonometric case. And so I will review some basic known facts about eigenfunctions of the Ruijsenaars Macdonald operators in the trigonometrics. And after that, I will discuss formal eigenfunctions for this elliptic Ruijsenaars operators and give some comments on this. And if I have time, I will mention some relationship to Ruijsenaars' non-stationary Ruijsenaars functions. Okay, so is everything clear for now?
Yes, I believe
Yes,
so.
you can. Yeah. So the first page one, the elliptic Ruijsenaars difference operator, what are they? So I'm using, wait a moment, please. Oh, sorry. Yes. It's not very easy, but I will try. Oh, how the pointer work? If I want to use the pointer, I have to stop the screen for screen mode.
There's a laser pointer symbol.
Yeah, but I cannot use this in the for screen mode.
Ah, I see. Yes.
Wow,
That's okay.
This is already fine.
Yes.
So
go ahead.
I'm using. This is a standard notation of the p-shifted factorial. I am using p basis, p and q, and p is p stands for the elliptic norm. It's an exponential 2 pi I tau, if you wish. And q is a base for the q-shift operators. And so this is the standard notation of a p infinite product. And I use this notation of theta functions in the multiplicative variables. It's a product of c semicolon p infinity times p over z semicolon p sub infinity. And this combination is essentially the same as this up to multiplication by g to the power minus half. This is the same as the odd Jacobi theta function written in terms of multiplicative variables. But anyway, so by using this Jacobi theta function, I define operators d sub x and in upper script with parentheses r. In the parentheses, you have r from r01 up to n. This is the definition of this operator. It's a summation over the subsets of the index set 1 through n with cardinality r. And these are the coefficients. It's a ratio of theta functions. And also here you have the Q-shift product of Q-shift operator. Q-shift operator is defined in this way, just shift the variable xi multiplicatively by q. And maybe it's better to explain this operator a bit more. So that's the reason I wanted to use this. And for r, I will write down the operator for r equals 1. So then this is d1 rx. And in elliptics, I'm using this p in the parentheses here like this. This is a summation over I running from 1 through n. And here comes the product, j not equals to I. And here comes theta, t times xi over xj. I think it's good to write in this way to slow down the talk. So this is the ratio of theta functions. And here you have the, so this is the operator for the first order operator in this family. And so d0 xp is just 1. And so the top operator in the top degree is just the t to the power n choose 2 times t qx1 through qxn. So this is a kind of, this part is the Euler operator, counting the degree operator. And in the limit when p tends to 0. So p tends to 0 limit is the trigonometric limit. And in the p tends to the limit, this operator d1, in this case, I use the ordinary d, and this operator is product of j not equal to 1. And in this form, txi xj over, sorry, and tq xi. And also this part can also be written as a txi minus j over xi minus j. So probably many of you are familiar with this operator. It's a first order Q difference operator for which the McDonald functions are, McDonald polynomials are Eigen functions. All right. Any questions? Okay. So I go back to this page. So this, so I defined a family of Q difference operators in this way. And this operator is a one form. So the appearance of the operators can vary variously and vary depending on the choice of the gauge. But if you have one gauge, this is the commuting family of difference operators introduced by Simon Ruijsenaars in 1987. And it means that these Q difference operators commute with each other. So one of the main questions given such a family of commuting family of difference operator is to describe the joint eigenfunctions, simultaneous eigenfunctions in an appropriate space of functions. So this means drxp applied to psi of x semicolon p should be epsilon rp times psi xp. So these are the eigenfunctions, and these are the let's say eigenvalues. So the main question is to describe the. There are lots of works about this type of commuting family of difference operators, and also let's say algebraic construction of such a commuting family of operators. But it seems not much is known about the analytic aspect, eigenfunctions. So the main question is this: to analyze, to describe the eigenfunction, this commuting family eigenfunction, joint eigenfunctions for this commuting family of operators. So I first review some known facts in the trigonometric case that is related to the McDonald theory. And after that, I will discuss the perturbative eigenfunctions in the elliptic case. By perturbative, I mean eigenfunctions. It's an eigenvalue problem in which the eigenfunctions and eigenvalues can be expressed. They are expressible by means of power series of P. So that is the meaning of the perturbative I'm using. Okay. So I go to the trigonometric case. So as I already mentioned, and in the trigonometric case, in the limit as P tends to 0, the elliptic Ruijsenaars operators reduce to this much simpler form. And okay, so I gave a remark on how these coefficients, sorry, no, it's coming down. Wait a moment. You can use the pointer only in. Oops. here. How, what is the origin of these coefficients? So if I use the notation delta of x to for this difference product, xi minus xj, product of xi minus xj's over the indices of this type. And then if you apply the t difference operator, you apply t shifts in the to the variables whose indices belong to I, then the ratio of this form gives this expression of the coefficient. So these operators, Ruijsenaars of McDonald's, as well as the elliptic Ruijsenaars operators, are related to difference product or p deformation of the difference product. And also I gave some comments here. For those who knows the notation of representation theory, it's a trivial, just a standard notation, but maybe I will remind you that lambda is a notation for a vector of integers, lambda 1 through lambda n. And if you know, use canonical basis epsilon and denoted as epsilon I, this is related. This is written as this, and the set of such multi-indices with integer entries is denoted by P, and in representation theory, this P is called the weight lattice of the general linear algebras. And also for each multi-index of this type, we associate a monomial, x to the power lambda, which is a product of x1 to the power lambda 1 through xn to the power lambda n. It's a multi-index notation. And also, if you work on the representation theory, you will use formal exponentials e of lambda. It's an exponential 2 pi minus 1 lambda when you regard lambda as a linear function on the Cartan subalgebra. But this is the same thing as x to the power is the same thing as this. Okay. Having said this, I will recall some results about McDonald polynomials. So in the framework of McDonald's polynomials, in the theory of McDonald polynomials, it is known that the parameter t, if the parameter t is generic, then these Q difference operators can be diagonalized simultaneously. And on the ring of symmetric Laurent polynomials. Maybe I should have, wait. No, oh, yes, wait a minute. So this notation C x plus minus 1 is for x1 plus minus 1 up to x minus n plus minus 1. This is the notation for the ring of Laurent polynomials, finite sum of monomials having negative exponent as well, and allowing the negative exponents. And so this Sn, this means symmetric Laurent polynomials. Okay, and so then, okay, sorry. Oh, it's going up. So the integral weight is n tuple of integers, as I said already. Among them, we looked at such indices having, sorry, wow. It is not coming down. Oh, yes. Yes, those having indices n tuple of integers, which is a non-increasing sequence, is called a dominant integral weight. So such a non-increasing sequence of integers is related, it enters in describing the Eigen functions here. And such objects are called dominant integral weights, and we denote by P plus this cone of dominant integral weights. And also in this weight lattice, we have a so-called dominance ordering. It's a partial ordering. Define, I recall the definition, but if you don't care, that's so. Yeah. Maybe if you are not familiar with this type of ordering, you can just think of the lexicographic ordering of the multi-indices. But anyway, so I suppose that this parameter t, it's a coupling constant. It's a generic in the sense that t to the power k is not the integer power when k equals 1 up to n minus 1. So that's the genericity condition. Then you can show that for each dominant integral weight is n tuple of integers satisfying this condition, and there exists a unique symmetric Laurent polynomials, which I denote p sub lambda of x, satisfying these two properties. The first condition 0 is it has a leading term x to the power lambda, and the rest is finite sum of the lower terms with respect to the dominance order. You can replace this condition by the lexicographic order, if you like. But anyway, just this is and the coefficient of the leading term is normalized as 1. This is a normalization condition as well. And the condition 1 is that this Laurent polynomial should be Eigen functions simultaneously for these commuting family of McDonald-Ruijsenaars operators. So for each dominant integral weight, there is a unique normalized McDonald polynomials, monic McDonald polynomials, which is a joint Eigen function for this commuting family of operators. So that is a theorem, and I give a remark that the eigenvalues, d sub lambda r, is in fact an R's elementary symmetric function. I didn't give the definition of the elementary symmetric function, but maybe I will write the elementary symmetric function definition. ER, maybe I will, S1 through Sn. This is just an ordinary elementary symmetric function. Si1 up to SIR. So this is the elementary symmetric function. And what's that? Okay, and let me see. Okay, go back. And then, and also, so from this condition of triangularity with respect to the dominance ordering, you can show that these McDonald polynomials, P lambda x, form basis as a vector space of the ring of symmetric Laurent polynomials. It's a kind of completeness of the Eigen functions. Okay, this is the fundamental theorem on the McDonald polynomials. So I think I have to finish at 11, 12 or 15, maybe 15 or 55.
55.
55, okay. Still, okay. Then, so McDonald polynomials have many remarkable properties that can be found in the textbook of McDonald. It was a reference to, and so I recall some properties, two of the properties of the McDonald polynomials here. And the first one is an explicit formula. It's a combinatorial formula, and if the last entry of this lambda n is non-negative, it's called a partition. So dominant integral weight is called a partition. And if it's a partition, it can be written as a sum of monomials with some coefficients, and over all increasing sequences of partitions, starting from, this is empty partition, zero partition, starting from going up to lambda by n steps, and with coefficients which are called the so-called Peary coefficients. It's the explicit form of the Peary coefficients are given here, and they are defined. It's a rather complicated formula, but it's a rational function expressed in terms of Q-shifted factorial. Yes, factorials. And these coefficients are non-trivial only if the lambda over mu or lambda minus mu is a horizontal strip. I will not explain what is a horizontal strip, but also, so for this reason, so this summation over the sequence of increasing sequence of partitions can be interpreted as a summation over the set of the so-called semi-standard tableau of shape lambda. So I will not explain the combinatorial terminology here, but so this expression is sometimes called the tableau representation or the McDonald polynomial. Another thing I would like to mention is the self-duality. This self-duality is a very characteristic feature in the trigonometric McDonald theory. And so we normalize P lambda, dividing it by the value at P t to the power rho. T to the power rho is just means, I'm using the notation rho to refer to, in this sense, it's a staircase partition. So this is Tn minus 1, Tn minus 2, and so on, to 1. So, so this is a kind of a different base point in the theory, and we normalize P lambda. So by dividing the value at this point, so that this P lambda tilde x takes value 1 at this point. Then surprisingly, if after this normalization, this polynomial becomes symmetric with respect to lambda and mu, you can exchange. If you exchange the lambda and mu, the result is the same. So this means that mu is a kind of position parameter, position variable, and lambda is a kind of spectral parameter, spectral variable. So there is a symmetry in between position variables and spectral variables in this McDonald polynomials. That is one characteristic feature of the McDonald polynomial. Okay, that is yes. So this is about eigenfunctions starting from x to the power lambda. So lambda is when lambda is a dominant integral weight, this is a theory of McDonald polynomials. And so what I'm going to do is to just replace this lambda to a generic complex weight. This means P tensor CZ. Simply, I assume that I consider this the cases where the lambda is a complex, arbitrary complex numbers. So even in such cases, it is known if lambda is generic, there is a very characteristic eigenfunctions which are called asymptotically free joint eigenfunction with leading term. So this is a plane wave term, and which is convergent in this region. And such a function is such an eigenfunction is called asymptotically free solution. So I formulate this kind of things following this paper with Shiraishi in 2012. And so the fact that you are working on this asymptotic domain corresponds to considering the formal power series of x2 over x1, x3 over x2, and so on, up to xn over xn1, assuming that the absolute value of these things is very small. So I just replace them by formal power series now. Then you can consider a function inside this vector space, formal things. So that is a asymptotically free solution. So instead of having lambda, I look only at this main body belonging to this formal power series ring, and using this x variables and the dual variables, sorry, S1 through Sn, I try to find the formal power series in this ring, in this ring, with coefficients, whose coefficients are rational functions in S. Then you can show that there is a unique power series of this form, and with leading coefficient 1, such that after multiplying x to the power lambda, the plane wave factor, it becomes a joint eigenfunction of the McDonald-Ruijsenaars operators. And so the eigenvalue also have the same type of expression after identification of the spectral variables S with the t to the power or q to the power lambda, as I mentioned already. So such an object is called the McDonald. We call such an object fxs, the McDonald function in the asymptotic domain here. So asymptotic domain means this eigenfunction can be expressed. The essential part of this eigenfunction can be expressed as a power series of these variables. That's the meaning of this asymptotic domain. Okay, so this McDonald function has a very remarkable properties. And you wait a moment, 55. So, and as in the case of McDonald polynomials, this power series also have a very nice combinatorial formula. So the formula itself is complicated. I will not explain anymore now. But when lambda equals to, lambda is a dominant integral weight, then the original McDonald polynomials can be recovered as a product of x to the power times lambda and times f of x with s specialized to this t to the power of q to the lambda with lambda dominant integral. And so this is and this formula recovers the combinatorial formula, tableau representation of the McDonald polynomials. Namely, I'm mentioning that. So this McDonald function in the asymptotic domain I'm referring has also have an explicit formula corresponding to the tableau representation of McDonald polynomials. That is one thing. Another thing is the symmetry. If you normalize multiplying an appropriate factor in S variables, and then it becomes symmetric with respect to S and X. This time X is the position variable, S is the spectral variables. So you can keep the symmetry between this. This is a kind of bispectral self-duality, even in this McDonald function level. And next page, I will not mention this here. And also, as to the regularity, we can say very strong statement, give a very strong statement. It's this function can be extended to a meromorphic function on the whole algebraic torus. And in the variable x and s, And actually, we can explicitly specify where the poles are located. I mean, these are location of poles. So the pole factor is a product of Q-shifted infinite products written in this way. And if you multiply this denominator to this function, this is regular, and it's an entire function and on the algebraic torus. It means it's a copy of C stars. And yes, so, and also this keeps the symmetry in between X and S. Also, you have symmetry between exchanging T to Q over T also. So that is the main feature of this McDonald function in the asymptotic domain. I now go to this elliptic case. One remark about this, you already saw this definition of Ruijsenaars operators. And even in that case, if you introduce P deformation of a difference product appropriately, yes, I thought I should have said this kind of things before, but if you have this expression, P infinity, P over Z semicolon infinity, this goes to just 1 minus T when P goes to 0. So if you form a product of theta functions of this form, in the P equals 0 limit, it recovers the ordinary difference product. The reason I'm mentioning this in this context is the coefficient of these Ruijsenaars operators can also be written as a ratio of P deformation of difference product, a ratio between these two things. One applied, yes, just see this formula. And also, I want to give a remark. This P deformation of the difference product is essentially the Weil-Katz denominator for the affine D algebra GLN hat, except for a factor coming from the fundamental weights. But it is essentially the Weil-Katz denominator. And reflecting this fact, this object, this can be expanded in terms of power series as well, but it can be regarded as a formal power series here. So this part, x2, 1, x1, corresponds to the first simple root, and this corresponds to the nth simple root. If you add another monomial, p x1 over xn, this corresponds to the zeroth simple root of the affine root system. Then, so this denominator belongs to this rings of formal power series. So in the analysis of Ruijsenaars operator, this ring of formal power series plays a very, very important role. Okay, having said this, I go to the existence of formal Eigen functions in the elliptic case. So you can show that elliptic, So I mentioned you have a commuting family of difference operators. This is elliptic Ruijsenaars difference operators. You can show that these operators act on this ring of formal power series with coefficients in the ring of symmetric Laurent polynomials. So it is not obvious, but you can show this, and you can try to diagonalize simultaneously these Ruijsenaars operator. The answer is given here. So suppose that the parameter t is generic as before, then for each dominant integral is in the same condition as in the case of McDonald polynomials. This initial value problem, so there should be Eigen functions, joint Eigen functions for the elliptic Ruijsenaars operators, and at p equals 0, they should recover the ordinary McDonald polynomials, and the eigenvalue should also be the eigenvalue for the McDonald operators. So this eigenvalue problem has a essentially unique solution. Actually, eigenvalue is unique. Eigenvalues are determined uniquely from the operators, but you are looking at the Q difference equation, and P is a kind of constant with respect to the Q shift. So so P lambda XP is determined uniquely up to multiplication by a formal power series in P. I'm regarding P as a variable now. And also, you can say something about the poles condition of pole conditions of the coefficients. But anyway, there are essentially unique formal P extension of McDonald's polynomials. That is a statement. How many minutes do I have? 5 minutes.
Yes,
Okay.
5 minutes.
Okay. Then I go to the elliptic analog of the McDonald function. In this case, it's essentially you need to set up an appropriate ring of formal power series on which the McDonald Ruijsenaars operators act, and such formal power series related to the asymptotic region in some way. But anyway, so I wrote this kind of things, but you can try to find this fxsp, p deformation of the f function that I mentioned before, so that after multiplied by the plane wave factor, this becomes a joint eigenfunction of this commuting family of Ruijsenaars elliptic functions. So in this ring of formal power series, you can find a unique, essentially unique function. So this initial value problem has a essentially unique solution. Eigenvalues are determined uniquely, and formal power series is determined up to multiplication by some power series only in P. So this is two theorems gives for existence of formal eigenfunctions and formal eigenvalues that corresponds to the McDonald polynomials and the McDonald function in the asymptotic region. So finally, I would like to mention the result about the convergence of formal eigenfunctions. So I will state this theorem F first. So for generic complex weight lambda, the normalized, I will not mention about the normalization here. The normalized formal solution with S equal T to the power rho times Q to the power lambda of the initial value problem. So I mentioned this problem has a formal solution, but it is absolutely convergent in this domain. So x2 over x1 should be smaller than epsilon, absolute value. And at the last part, I add some this condition. Px1 over x, and absolute value of this one should be less than n epsilon. So this is a very, very small region on the boundary. And I would say, well, yes. Oh, wait a moment. Yes, I should. So we are looking at this condition means that we are looking at this asymptotic region, xt, and so on, x7, and the last here. So it's these conditions specifies in which circle x1 through xn are located, and there is it's a kind of far distancing condition, and the ratio of these radius should be small, and so this is a convergence result for this, and this can be recorded as a Ruijsenaars function in this asymptotic domain. And also, I have put a question mark here, but you can show that the formal solution corresponding to the P deformation of the Macdonald polynomials also convergent in some region, some domain near the real torus. So the reason I just put I put question mark here is this result is very recent, and maybe require some final check. So for safety, I just put this question mark. But you also have this kind of convergence result for the elliptic deformation of Macdonald polynomials. I think this question mark should be removed very soon. So it's 5:55, 1 minute past. So maybe I will stop here and call for questions. Maybe.
Great. Thank you very much, Professor Noumi. I want to ask the participants to either raise their hands in the participants box or put their question in the chat box. And while they're looking at how to do that, perhaps I could ask you a question.
Yeah.
I wanted to ask about, it's a very interesting idea to me, and please forgive me because I'm not as familiar with the notation for these functions as you are. This question of defining an initial value problem with initial value given at p = 0.
Right.
This is a little bit surprising to me because every now and then, of course, you are dividing by p as well. For example, in the statement of theorem E at the bottom, you have a division by p, or the norm of p, on the right-hand side of the inequality. So how does one get away from that? If we're looking at p very close to 0, this is a very large annulus.
Yes. It finally becomes the whole algebraic torus.
Right.
Product of C star. And actually, Macdonald polynomials are Laurent polynomials. They are entire function. So this range of convergence becomes larger and larger as the absolute value of p tends to 0. Right. And to cover the whole space. That's the picture of this theorem.
Okay. Right. Thank you very much. Are there any other questions or comments? Ole, maybe you can bring the camera down so we can see you better.
Sorry, yes.
Great.
Thanks for an interesting talk. I have a question. We, of course, have, well, I mean, we don't call them elliptic Macdonald functions, but in the BCN case, essentially the theory that was developed by Eric Rains.
Right.
Now, in the classical limit of that theory, you can also recover the Macdonald polynomials. So essentially, I mean, you can't do this at the elliptic level, but if you first set the norm to 0, then essentially degree terms of that theory will give you back type A, even though you're working in BCN. Would you expect that there's any connection between your sort of formal asymptotic solutions and the work of Eric Rains?
Well, the basic idea of mine and my co-workers is to respect the Ruijsenaars difference operators, right? They should be eigenfunctions for them. That is I would say, that's the basis of our work. So it is not clear how the Eric Rains work is related to the original Ruijsenaars operators, but there should be, in my opinion, there will be many ways, many streets where you can enter if you go to the P world, elliptic world. And I'm not sure yet, but if you, on this level of a stationary Ruijsenaars function, it may be difficult. But if you introduce some extra parameter, which is denoted by kappa by Shiraishi, taking care of the so-called time dependence or time-dependent Ruijsenaars equation. That should be non-stationary Ruijsenaars equation. There is no fundamental equation for this non-Ruijsenaars function, but the Ruijsenaars has proposed the answer should be this way. So, but anyway, if you go up to the non-stationary level, so by fixing some parameters, so maybe you can, there is a way to specify your Ruijsenaars function is here, is in this limit, range function is in this limit, and some other people calling elliptic Macdonald should be here, or that is my vague understanding.
All right, thanks.
Okay, sufficient for your question?
Yeah.
Thank you. Any other questions or comments? I don't see any raised hands, but please don't be shy.
Dajun.
Dajun, yes.
Yes, Noumi Sensei, I have a very naive question.
Yes.
Could you introduce some connection between elliptic Macdonald polynomials and binary equations?
Perturbative. It's a very good question.
Are there any connection between them?
Wow, so yeah, it's a too good question to. So I cannot answer. In some way, I recently wrote a paper with Simon Ruijsenaars and Yasuhiko Yamada on the relationship, a Calogero Poundable type relationship in the BC1 case. So there may be some connections of this type, Calogero Poundable correspondence, even in this A-type case. But I haven't worked on this, and I'm not sure about this yet. Maybe you could try.
That's okay, thank you.
Okay.
So if there is no further questions or comments, perhaps I'll remind everybody that this talk has been recorded and the video should be available on the APIOS website or on YouTube, I hope. And when it is ready, we will let you know if you're on the mailing list. So please make sure that your email is on the mailing list, and send an email to Giorgio Gubbiotti, if you'd like to join the mailing list. So let me now thank Professor Noumi for a wonderful talk. I learned a lot in this talk. I am not so familiar with, as I said earlier, with this world of special functions and quantum integrable systems. So I'm really grateful for a very accessible talk along these lines. So thank you very much indeed. Thank you.
Thank you very much, Nalini and Giorgio.
So I guess it's now time to leave. We had 79 participants, which is must be a record. Must be a record for an integrable system seminar that I know.
Yeah. So I think I'm stopping the recording now, and later I will put it on the website.
So there are many people now starting to put comments in the chat saying thank you for your talk, Noumi Sensei.
Thank you very much.